So in this problem, you're asked to draw a resonance structure of this cyclopentadienyl radical. And maybe one of the issues is this overlap of these arrows. Again, I'm not completely sure, but if you were asked to draw this second structure here, that would not be the correct resonance form from what you're starting with. So if you were starting with this allylic radical, so this is doubly allylic, and then from your first arrows, you're showing this moving here, then the pi bond, and then the radical ending up at the 3 position. So the second structure should look like this. I'm not sure how many other structures it wants to show, but if you were to continue on, that would be another resonance form there. And then you could keep going and draw a couple more from that. But again, I'm not sure if it has to do with these arrows overlapping here, if that's an issue with the computer. But if you were drawing this, that's not the correct resonance form from what results from that arrow. So on this second one, basically you've done the substitution, the CH substitution, so that's not the correct location. So in this radical halogenation problem, what you're asked to do is identify where the alkene is. So the alkene's right here, and then the carbon's bonded to that alkene. So this one, and I'll use little squares. So the circles are this identical allylic carbons, and then the squares are identical allylic carbons as well, bonded directly to the alkene. So our key, there's no H's bonded to those. So those are the squares, there's no H's. The circles, those are methyl groups, so those have allylic hydrogens that can be substituted, and that's what you're looking to do. So the mechanism of this reaction is that you're forming an allylic radical. And so if you consider what are the resonance forms for that allylic radical, now those are the positions where you can get substitution. So if you just draw those two products out, so what you have to pay attention to in this type of problem is the allylic resonance is what's important, because it's easy to sort of forget that there's resonance and not get the remaining products. So first thing, identify the allylic positions. Second question, do they have hydrogens? If yes, then you'll form an allylic radical there, then draw the allylic radical resonance, and then those are the positions that will substitute. So this last one, you're given an alkene. So I'm highlighting the alkene in green. So it's a differentially substituted alkene. So basically here you have H, then H, and then the other position you have carbon and carbon. And so what these conditions do, this is called a peroxide, that will cleave under radical conditions to give you two of this type of radical. So an alkoxy radical. That will then react with the HBr. to form an alcohol plus a bromine radical. That bromine radical is what is going to participate with the alkene. So I'm just going to draw that. So now you have two choices of which carbon that radical can add to. And so it's going to add to the least substituted, which I'll show in red. It adds to that because after it does that, it generates a more stabilized or more substituted carbon radical. So let's draw that out. So now we have a tertiary radical. That tertiary radical will then react with the HBr to propagate the chain. And so you're ending up with the least substituted bromine. So this is a primary bromide. So conversely, if the radical were to add to this carbon, you'd get a primary radical. So radical stability follows this trend. And so that's why we're making that decision at that point to add the bromine to the less substituted carbon to get the more substituted carbon radical that's then quenched with hydrogen to give you the least substituted alkyl bromide.